Okay, so let's discuss the second law of thermodynamics. So the very famous Cambridge writer, C.P. Snow, compares the second law of thermodynamics to William Shakespeare, the works of William Shakespeare. So, because sometimes he would be at parties and people would like talk about certain works of literature, and they would say, "Oh, if you haven't," and you would be seen as not very sophisticated if you hadn't read, I don't know, Hamlet or something like that. And then C.P. Snow would ask, "So, do you know the second law of thermodynamics?" And he would draw a blank. People would not know. And according to him, what he was asking them is the scientific, version of Shakespeare. Have you read any work by William Shakespeare? So everyone should know the second law of thermodynamics. Okay, so I want to give you a little bit of a background. And the background is this, because we're doing statistical mechanics, is that it is an observation that the microscopic laws of nature are time reversible. Although the Schrodinger equation looks very much like a diffusion equation. So you saw how to derive the diffusion equation in one of the tutorials. Remember that? The diffusion equation was the first order time derivative of something. Then there was a diffusion constant, and the second order space derivative of that same for something, right? And of course, the diffusion equation has time built in. If we say, take a cup of, like a glass of water, and we drop like a red dye, we see slowly through diffusion that the whole glass of water become, red. And that's, of course, controlled by the diffusion equation. The diffusion equation, you never see the drop of water becoming, the red, the water becoming like clear, and the dye sort of coalescing into a drop. So the diffusion equation does have time built into it. The fundamental equation in quantum mechanics is called Schrodinger equation, and the Schrodinger equation is very similar looking. It's a first order in time, and if I ignore, say, some potential, which it's for free particle, that's fine. It's actually looks exactly like the same. However, the Schrodinger equation is actually a complex equation. It has I in it. And these wave functions are complex functions. A result of this is that the Schrodinger equation is a time reversible equation. Because here, if you put t equals to minus t, you get a different equation. But in the Schrodinger equation, if you put t equals to minus t, and then you complex conjugate it, then you get the same equation, but for psi star, which is another way of saying that if psi describes a function moving forward in time, Psi star describes a function moving backward in time. All of this to say is that the microscopic world, the physics, is time reversible. Yet, at a macroscopic level, we see that the world has a very specific arrow of time, right? So, microscopically, the arrow of time is ambiguous. But macroscopically, we see that the arrow of time is very well defined. Right? So for example, we don't see broken eggs mend themselves spontaneously, right? Hence the tragedy of Humpty Dumpty, right? The whole point of Humpty Dumpty is that he was messing with the second law of thermodynamics. And then we don't see coffee at room temperature, which has cooled down to room temperature, spontaneously becoming piping hot. Or if you have a melted ice cube in a drink, it doesn't, if you had melted it, it doesn't suddenly appear. So on a macroscopic level, we see that time has a certain direction. So the emergence of the arrow of time is intimately connected to the second law of thermodynamics and the idea of entropy, okay? So the arrow of time in microscopic physics, in macroscopic world, is intimately connected to the second law as formulated in terms of entropy, okay? And that's what we want to understand why. So this is just to kind of, motivate you, is that the second law of thermodynamics and entropy are perhaps the most important concepts in all of theoretical physics. Okay, before we go to such lofty stuff, let's look at a more old-fashioned statement of the second law. But before we do that, any questions?
No,
All
sir.
right.
So
All right.
are the
So
second law and third law both related to entropy?
I think, yeah, third law does, entropy does play a role in it, but I can't recall exactly what the third law is right now. But
Okay, sir.
the time, the arrow of time is actually really only related to the second law and how entropy can change. And from a, once you understand statistical mechanics, it just seems obvious. Okay, the second law is obvious. All right.
Yes, sir.
Okay, so old-fashioned statements are statements of the second law. So this was, so these statements were made independently by two people, and one was Clausius. And what Clausius says was the following: no process is possible whose sole effect is the transfer of heat from a colder body to a hotter one. Okay. So here, like the sole effect is important, because obviously we all own a machine that can do this. It's called a fridge. Can transfer heat from a hot body to a like a I don't know, a cold body to a hot body. But that's not the sole effect, right? Sorry. Yeah. And then Kelvin had a different version of it. And at some point we'll prove that they're equivalent. And Kelvin said that no process is possible whose sole, they're all very interested in souls, whose sole result is the complete conversion of heat into work. Okay, so these are the two different definitions of two different statements of second law.